1 minute ago, the Philippines crossed a threshold that meteorologists have been dreading for days. Super Typhoon Uwan, internationally known as Fung-wong, has made landfall over Dinalungan in Aurora Province with the full force of a Category 4 equivalent storm. At 9:10 p.m. local time on November 9, 2025, the typhoon's eye wall struck the northeastern coast of Luzon with sustained winds measuring 185 kilometers per hour and gusts reaching 230 kilometers per hour, velocities powerful enough to strip roofs from reinforced concrete buildings, uproot century-old trees, and turn everyday debris into lethal projectiles. Infrared satellite imagery from Japan's Himawari 9 satellite captures the storm in terrifying detail. A tightly wound circulation with a well-defined eye, surrounded by a ring of towering convective clouds with tops so cold they glow white on thermal sensors, indicating explosive vertical development reaching into the upper troposphere. Coastal Doppler radar installations, still operational despite the mounting chaos, are detecting storm surge heights between 3 and 5 meters, inundating low-lying communities. This is not hyperbole. This is the raw mathematics of atmospheric violence translated into human consequence. But the storm that just slammed into Aurora didn't appear overnight. Just 6 days ago, on November 3, meteorologists at the Joint Typhoon Warning Center began monitoring an unremarkable area of low pressure approximately 560 kilometers northeast of Chuuk in the Federated States of Micronesia. Within 24 hours, that disturbance had organized into a tropical depression. By November 4, it earned the name Fung-wong from the Japan Meteorological Agency. Then something remarkable happened. The system encountered a corridor of extraordinarily warm ocean water. Analysis of sea surface temperature data from the region indicates temperatures exceeding 29 degrees Celsius, with the warmth extending to significant depths. This pattern is characteristic of the Western Pacific warm pool during favorable conditions. This massive reservoir of thermal energy became fuel for an atmospheric engine that would intensify with shocking speed. By November 8, the Philippine Atmospheric, Geophysical, and Astronomical Services Administration classified Uwan as a super typhoon. The storm had achieved this transformation in less than a week, traversing thousands of kilometers of the Philippine Sea while gathering strength with each passing hour. Rapid intensification, meteorologists call it, and Uwan exemplified the phenomenon. The storm's central pressure plummeted to 935 hectopascals, its circulation tightened, and its eye wall became a perfectly symmetrical ring of destruction visible from space. The science behind this explosive development reveals just how perfectly aligned the atmospheric conditions were for catastrophe. Tropical cyclones are heat engines, converting thermal energy from warm ocean water into kinetic energy, the spinning winds that define these storms. For rapid intensification to occur, multiple factors must align simultaneously. First, sea surface temperatures must exceed 26.5 degrees Celsius, but that's merely the minimum threshold. Satellite observations indicated Uwan traversed waters where temperatures reached 29 to 30 degrees Celsius, with the warmth extending well into the water column. This depth matters critically because as the storm's winds churn the ocean's surface, they normally mix cooler water from below upward, creating a negative feedback that limits further intensification. But when the warm layer is deep, as conditions suggested across Uwan's path, this cooling effect is suppressed. The storm keeps feeding on thermal energy without restraint. Second, atmospheric conditions must cooperate. Uwan encountered minimal vertical wind shear, meaning the winds at different altitudes moved in nearly the same direction in speed, allowing the storm's circulation to remain vertically stacked and efficient. Third, abundant mid-tropospheric moisture provided the raw material for intense convection.
Research published in the Proceedings of the National Academy of Sciences has documented that upper ocean temperatures in the low-latitude northwestern Pacific now control the rate of typhoon intensification, and those temperatures have been anomalously warm. Climate attribution studies indicate these warm conditions have been made up to 40 times more likely by human-caused climate change. Uwan didn't just happen, it was statistically primed by a warming ocean. The sheer scale of Super Typhoon Uwan staggers comprehension. At its peak intensity, Pagasa estimated the storm's diameter at 1,800 kilometers, a circulation so vast that it covered nearly two-thirds of the entire Philippine archipelago. To put this in perspective, strong to typhoon force winds extended 900 kilometers from the center. This meant that even regions hundreds of kilometers from the eyewall experienced dangerous conditions. The outer bands of Uwan were affecting areas from the Visayas to Mindanao, despite the core of the system striking northern Luzon. Satellite-based precipitation mapping, using technology similar to NASA's Global Precipitation Mission, would have tracked the storm's moisture plume stretching more than 1,200 kilometers, extending towards Taiwan and the South China Sea. This enormous atmospheric river carried with it the potential for catastrophic rainfall across multiple island groups. Historical records from Pagasa show that while the Philippines experiences an average of 20 tropical cyclones annually, Uwan marked the 21st storm of 2025, already exceeding the typical annual count. And unlike many typhoons that weaken before landfall due to cooler coastal waters or unfavorable wind patterns, Uwan approached the coast near or at its peak lifetime intensity. Meteorologists monitoring the storm noted that this maintenance of strength through landfall had ominous historical precedent. The destruction wrought by storm surge unfolded with terrifying speed along the Aurora coast. Storm surge isn't simply high waves, it's a sustained elevation of sea level driven by the storm's powerful winds pushing water toward shore. Physics demands this water goes somewhere, and when it encounters a gently sloping coastline or funnels into bays and estuaries, the surge amplifies dramatically. Coastal communities in Aurora, Isabela, and nearby provinces faced surges reaching 3 to 5 meters above normal tide levels. For context, a 5-meter surge is equivalent to standing water reaching to the second story of most buildings. Entire neighborhoods found themselves submerged. Historical accounts from similar typhoon landfalls suggest that storm surges of this magnitude can inundate coastal areas within the span of 30 to 60 minutes, often giving residents limited time to reach higher ground. Simultaneously, the rainfall intensified to catastrophic levels. Pagasa weather stations recorded sustained rainfall exceeding 400 millimeters in 24 hours across northern and central Luzon. In mountainous areas where Uwan's outer bands collided with orographic lifting effects, localized totals could have reached significantly higher amounts. Based on orographic precipitation patterns documented in previous typhoons interacting with the Sierra Madre, accumulations exceeding 600 millimeters in isolated pockets would be consistent with the atmospheric moisture content and terrain interaction observed. To visualize this, 400 millimeters equals nearly 16 inches of rain falling in a single day. Most drainage systems and river channels cannot accommodate this volume of water. Rivers overflowed their banks. Tributaries that normally flowed gently became raging torrents. Urban flooding inundated ground floors and stranded thousands. But the greatest danger emerged in the upland areas where saturated soils on steep slopes began to fail. Landslides, deadly cascades of mud, rock, and debris swept downslope, obliterating everything in their paths. By the time Uwan made landfall, the human toll was already mounting. More than 1.1 million residents across 12 regions had been evacuated in the preceding 48 hours, as authorities implemented forced evacuation protocols in high-risk areas. Emergency operations centers from the National Disaster Risk Management and Reduction Council worked around the clock, coordinating with local government units to establish evacuation centers and stockpile supplies. Despite these preparations, the storm claimed lives. Reports confirmed at least 4 fatalities as of the hours following landfall, drownings, structural collapses, and other storm-related incidents as the outer bands and then the core of Uwan swept across vulnerable areas. Power grids failed across vast swaths of Luzon and the eastern Visayas, plunging at least 184,000 customers into darkness. Communications infrastructure, cell towers, internet cables, radio repeaters went offline, creating information blackouts in affected areas. Transportation ground to a halt. Ninoy Aquino International Airport suspended operations. The Philippine Coast Guard restricted all sea travel, stranding more than 6,600 passengers, crew members, and cargo handlers in 86 ports nationwide. Rescue operations faced nightmarish conditions, near zero visibility from torrential rain and flying debris, impassable roads blocked by fallen trees and utility poles, rising floodwaters that made low-lying areas inaccessible. Emergency responders described a situation where the need for rescue was overwhelming, but the ability to reach victims was severely constrained. Agricultural damage began accumulating immediately, with initial assessments from Camar and Sur indicating over 6.38 million Philippine pesos.
For Filipinos, the parallels to Super Typhoon Haiyan, locally known as Yolanda, are inescapable and haunting. On November 8, 2013, exactly 12 years before Uwan approached, Haiyan made landfall in Guian, eastern Samar, with what may have been the strongest winds ever recorded for a landfalling tropical cyclone, 315 kilometers per hour, according to the Joint Typhoon Warning Center. Haiyan killed at least 6,300 people and displaced 4 million more. The storm surge in Tacloban reached heights estimated between 7.5 and 9 meters, a wall of water that swept entire neighborhoods into oblivion. In terms of raw wind speed at landfall, Uwan measured slightly weaker than Haiyan's apocalyptic peak. But in terms of aerial extent and rainfall distribution, Uwan presented different challenges. Where Haiyan's most devastating impacts were concentrated in a relatively narrow corridor through the central Philippines, Uwan's massive 1,800-kilometer diameter meant its destructive potential was spread across a far larger geographic area. The evidence from reported impacts suggests that Uwan's rainfall totals were distributed across multiple regions, creating widespread flooding concerns rather than the concentrated storm surge devastation that characterized Haiyan. This broader distribution meant more communities faced significant threats, even if fewer experienced the absolute worst-case scenario. Research published in the months following Haiyan suggested that climate change likely increased that storm's rainfall and intensity, with estimates ranging from 2 to 4 meters per second wind speed enhancement and increased storm surge heights. Similar attribution studies will undoubtedly examine Uwan in the coming months. As Uwan moved inland across Aurora, it encountered the formidable barrier of the Sierra Madre mountain range. This collision between a super typhoon and steep topography created conditions for catastrophic landslides and debris flows. The Sierra Madre, running north-south along the eastern coast of Luzon, functions as a natural shield that typically weakens typhoons as they move westward. The interaction works through mechanical disruption, mountains literally tear apart a storm's low-level circulation, and through the rapid loss of energy as the system moves over land and loses its ocean heat source. Paigasa forecasters correctly predicted that terrain interaction would cause Uwan to weaken significantly, though they emphasized they would remain at typhoon strength throughout its passage over northern Luzon. The rainfall, however, amplified dramatically. Orographic lifting occurs when moist air is forced to rise over mountains, causing it to cool and condense its moisture into precipitation. In Uwan's case, the abundant moisture in the storm's circulation encountered the Sierra Madre's eastern slopes, producing what meteorological principles would suggest were extreme rainfall rates, potentially exceeding 100 millimeters per hour in localized areas where convection was most intense. This rainfall intensity, combined with the sustained nature of the storm's passage, saturated mountainous soils completely. On slopes deforested or destabilized by previous storms, these conditions triggered landslides. Entire hillside liquefied and flowed downward, carrying trees, boulders, and soil in deadly slurries that buried roads, homes, and fields. The provinces of Nueva Vizcaya, Benguet, and the Cordillera Administrative Region face particular landslide risks due to their mountainous terrain and recent history of heavy rainfall from previous tropical cyclones. The fingerprints of climate change are becoming increasingly difficult to ignore in storms like Uwan. Multiple peer-reviewed studies have documented trends that align precisely with what theoretical models predict for a warming world. Sea surface temperatures across the tropical Western Pacific have increased measurably over the past several decades, with Climate Central's Climate Shift Index indicating that current warm ocean temperatures were made up to 40 times more likely by anthropogenic greenhouse gas emissions. Research published in Proceedings of the National Academy of Sciences found that upper ocean temperatures in the low-latitude northwestern Pacific now control the seasonal average lifetime peak intensity of typhoons. And these temperatures have undergone anomalous warming even during periods when global atmospheric temperatures plateaued. The result has been an increase in rapid intensification events, storms that gain strength faster than historical norms. Recent peer-reviewed research has identified a detectable increase in the probability of rapid intensification in the Atlantic, Northwest Pacific, and globally, with high confidence that this trend exceeds what natural climate variability alone could produce. For the Philippines specifically, the 2025 typhoon season has been relentless. Coming just days after Typhoon Kalmehi left at least 224 people dead and displaced over 500,000 others, Uwan represented the 21st tropical cyclone of the year, a frequency that pushes the upper bounds of historical norms. Scientists monitoring these trends emphasize that warmer oceans not only make individual storms more intense, but can also extend the typhoon season and shift storm tracks. The confluence of repeated storms hitting already saturated ground create cascading vulnerabilities that amplify damage with each successive event. In the hours following landfall, the scale of the disaster began to crystallize. Emergency operations centers reported 312 schools damaged across Bicol, Calabarzon, and the Cordillera Administrative Region, with the Department of Education estimating 20.2 million pesos needed for cleanup operations and 57.9 million pesos for minor repairs. At least 5,572 classrooms in 1,072 schools were being used as evacuation centers, temporarily housing displaced families while also preventing students from resuming normal education. Road networks sustained major damage. In Aurora, a section of the Baler-Casagoran highway was closed in Dipaklo after large waves breached the road and eroded the foundation. In Camarines Sur, falling debris blocked portions of the Calabanga-Tanambak road, while the Tanambak-Tamban and Tanambak-Goa roads were rendered impassable by landslides and flooding. Water levels at Laguna de Bay, Philippines' largest lake, reached 12.7 meters, exceeding the critical threshold of 12.5 meters and raising concerns about additional flooding in communities around the lake. In Albay province, authorities reported lahars, volcanic mudflows mobilized by heavy rainfall on the slopes of Mayon volcano. These lahars carried volcanic sediment down river channels, threatening downstream communities with burial under meters of mud. Agricultural losses mounted as rice paddies remained submerged, and corn crops were flattened by sustained winds. Initial estimates from just the municipality of Buhi and Camarines Sur indicated 6.78 million pesos in agricultural damage affecting more than 85 hectares of rice fields and 39 hectares of corn crops. These figures, collected within hours of the storm's passage, represented only a fraction of the eventual economic toll.
But even as Uwan began to weaken over the mountains of northern Luzon, meteorologists were watching its projected track with continued concern. Pagasa forecasts indicated the storm would move northwestward and then more northward through Monday and Tuesday, maintaining typhoon intensity as it crossed Luzon. Early projections suggested that by Wednesday, November 13th, Uwan could move toward the Taiwan Strait, with the potential for landfall on the western coast of Taiwan by Thursday. This trajectory meant the storm, though weakened from terrain interaction over the Philippines, could still pose a threat to Taiwan's agricultural regions and coastal cities. The prospect of a storm that had already devastated one nation impacting another within days underscored the transnational nature of these disasters. Climate models project that as ocean temperatures continue to rise, the geographic range of tropical cyclone impacts may expand poleward, potentially placing regions that historically experienced fewer typhoons at increased risk. Taiwanese meteorologists would be closely monitoring Uwan's remnant circulation and updating their forecasts as new data became available. The inherent uncertainty in storm track forecasting, typically accurate to within 100 to 200 kilometers at 48 hours lead time, but less precise beyond that, meant the communities across northern Taiwan needed to prepare for multiple scenarios. Would Uwan track north enough to miss Taiwan entirely? Would it make direct landfall, bringing the same wind and surge threats that Aurora experienced? Or would it graze the northern coast, spreading heavy rainfall across the island but sparing it the worst winds? These questions drove evacuation decisions and emergency preparations across the Taiwan Strait. The Earth does not negotiate. It does not offer warnings beyond what physics and observation can reveal. Super Typhoon Uwan, fueled by abnormally warm waters in an ocean system altered by more than a century of greenhouse gas emissions, has reminded us once again that humanity's relationship with the climate system is not abstract. It manifests in 230 kilometers per hour winds. It arrives as 5-meter storm surges that erase coastal communities. It falls as 400 millimeters of rain that turns mountains into avalanches of mud. The Philippines, lying squarely in the crosshairs of the Northwest Pacific Typhoon Corridor, has faced these storms for millennia, but the frequency, intensity, and compound impacts of storms like Kalmegi and Uwan within days of each other represent something new. Soils never have time to dry, infrastructure damaged by one storm becomes more vulnerable to the next, emergency resources are stretched beyond capacity. Coastal communities face the question of whether rebuilding in place remains viable. Scientists will spend months analyzing the data from Uwan's passage. They will run attribution models to quantify how much of the storm's intensity can be linked to anthropogenic climate change. They will study the rainfall patterns, the storm surge dynamics, the landslide triggers. But the people of Aurora, Isabela, Catanduanes, and dozens of other provinces don't need attribution studies to understand what they experienced. They know that the storms are changing, that the ocean is warmer, and that the future holds uncertainties their grandparents never faced. As rescue operations continue and the full scope of Uwan's destruction becomes clear over the coming days, one truth stands immovable. The planet's atmospheric circulation has momentum, and once perturbed, it does not quickly settle. The consequences of altering ocean heat content play out in real time, measured not in degrees Celsius on a chart, but in communities rebuilding from devastation, in families mourning losses, in nations mobilizing against an invisible enemy that accumulates energy in the depths of a warming sea. If this story left you watching the satellite loops late into the night or wondering what next season will bring, then subscribe and pay attention, because the Western Pacific doesn't care about our schedules, and the storms are already forming for next year.